Okay, so let's try some of the things we talked about in Colab. So we'll say this is PCA experiments, and we'll import the usual suspects. Obviously, we need NumPy. We'll also for this one, we'll also need matplotlib as usual. PyPlot should be enough. And import, also, we're going to import from scikit-learn. And we're going to import two things. Actually, we're going to, from scikit-learn, we're going to need some data sets. And also, the main thing, which is from sklearn, we're going to use its PCA implementation and its kernel PCA implementation, and those are under the decomposition package. So from import, I think we need PCA, and let's also get kernel PCA, and that should be enough. Okay, it'll import those. So initially, I'm just going to do standard or linear PCA, and we'll first get the data. So what I thought was be a nice thing to do is use the MNIST digits data set that's already kind of inbuilt into scikit-learn. So you can always we'll get digit data is from data sets that we imported. Let's see, I think it's called digits. Load digits, yeah. So we'll get that and take a look at it. So digit data when you look at it, there's a bunch of stuff. There's data, there's images. So it's a bundle of an array of vectors called data, and then an array of arrays called images, and then you have targets and target names. We actually did this in class, if I remember correctly, but I'll quickly go over it anyway. So, for example, if we just look at digits data, it's this array of vectors, and we can look at its shape. So there's 1797 rows, each one has 64 elements. And actually, if you look at images, it's basically the same thing. It has 797 rows, and it has 797 matrices, and each one is an 8x8 matrix. Just kind of notice that. Same thing. Data just gives these images as linear vectors. Images is the reshaped form that gives you an 8x8 bitmap. What we're gonna do is we'll use data, and let's take a look at one of them. So it's something like this. You get a bunch of things, and you can kind of a bunch of elements, 64 elements. You can reshape that into 8x8. That's how they're supposed to be. So these are pixel values for an 8x8 bitmap, and you can almost barely see the pattern here, right? The outsides are 0, and insides are, so there's like a circle of larger numbers here, so this is probably a 0 shape. And the good thing is we don't have to do that by looking at the array. Matplotlib has a nice method called imshow. We can just feed that thing into imshow and see what it looks like. Yeah, it is a 0. Just to make it a bit nicer, you can say the color map should be gray. Looks good. And if you invert the values, it should be black on white instead of white on black. So that's your 0. That's the 0th element. Let's look at the 100th element, for example. Seems like a 4. You can actually check what it's supposed to be using digit data again, target. And let's say target, what was it? The 100th one, that's a 4. So the 1000th one, for example, is an image of the digit 1. So let's look at the 1000th one. It's a kind of weird one. Let's look at the 1010th. That's a 5. Let's see if the label matches. Yes, it's a 5. Okay, so this is how the data is kind of given to us. And notice that essentially you get 64 elements for each data point, so it's 64 dimensional data, and there's a meaning to those dimensions. The first 8 is the first row of pixels, the second 8 is the second row, and so on and so forth. So normally, obviously, you would kind of no way to visualize this data all at once, because you can't simply plot a 64 dimensional thing. You would try to plot maybe the first dimension. Let's do a scatter plot of data. What was it? Digit data. And let's say we'll take the 0th column, the first pixel, top left, and the same thing. The second pixel, if you plot those, it doesn't look like anything. Let's pick something else. Let's say we took the 16th versus the 45th pixel. Again, you don't get anything interesting. So one thing PCA can do for us is look at where the most variance is between these digits. So for most digits, there's going to be a kind of area around it that's going to be painted in like a 0. Some digits will have the insides empty, so those pixels will have a lot of variance. So when you put this into PCA, it should be able to separate these digits for us on two-dimensional space. So how do we do this? First, we need a PCA object. If you look at the documentation for that, which it doesn't want to show me, let's do it like this. Okay, so PCA is the constructor for this object, and you can define the number of components you want, so how many principal components you need. If it's none, it will have the same number of components as the data. Copy true will actually copy the data kind of to separate array. It won't work in place. There's whiten, which will kind of normalize your data, even if your data is from, for example, the variance is 100 and it's varying from 10 to minus 10. It will kind of drop it down to, I think, between -1 and 1, and so on and so forth. And then the SVD solver, the singular value decomposition solver, is the thing that basically finds the eigenvalues from, remember, from PCA. Normally, the rest you could just leave as it is. It works generally fine for most data. You'll only have to go into what solver you use if you have some very kind of non-well behaved data that the solver cannot solve it or something, then you might have to go into those details. Whiten, again, I'll leave that as false. If you have different data sets that have widely different variances and you want to kind of plot them together or something, whiten might come in handy. So, and the end components I'm just going to leave as, take the whole, kind of, in our case, 64, because it's okay if it generates all components, we'll just use the first two. So I'll generate a PCA object. So you can do this two ways. You can create the object and immediately fit the data, or just create the object and then explicitly say fit on it. So right now this is an empty PCA object. It hasn't learned anything yet. You can use fit and give the data matrix you want to fit. In our case, that's digits, digit data's data thing, and we'll have it fit that. So it's already fit, and now we can look at things about it. So we can look at number of components. Obviously, number of components should be 64 because we gave it 64 dimensional data. Other things we can look at is how good the kind of how well each thing captures variance. So explained variance is over here. So it turns out, actually this is messy. Let me just np set options, I think. Some print options, precision. We'll just do with 3 digits of precision, and we don't want the I think it was called suppress, yeah. So we don't want this scientific notation for now. We'll just see the actual thing. Okay, so when you look at it, the first component is most of the variance, the second component has some, and after maybe, I don't know, first dozen components or so, maybe 20 components, it drops off pretty quickly. And you can see the individual components. So we can say components, and it will give us a list of 64 arrays, each one being principal components, and it kind of conveniently orders them in order of higher, kind of in order of decreasing eigenvalue. So the first one is the first principal component, the one with the highest eigenvalue. And when you look at it, you can see the weights. It turns out it has high weights in certain pixels. It's not something we can kind of see visually. One way to actually do this is, let's make a figure and use the first two principal components to actually plot this data. So for that, we'll create our figure. We'll say plt figure. This will create a new figure for us, just so we see the figure easily. It's not really tiny. I'll make it 10 by 8. That's with 72 dpi. That's 10 by 8 inches. It should be large enough. And then we'll say, okay, this figure is going to have axes. We'll give the axes names later on. So let's say AX, for these axes, draw a scatter plot of transformed versions. So the two principal, this same data, essentially digits, data, put this into, extract the first and second principal components and plot those. So we can say, for that, we use our PCA object from before, this P. We'll say P, and there's a nice function called transform, which will take our digit data and transform it into the PCA space, so do the correct rotation, and we only need the first component and the second component. Okay, so we'll say the second index, that's our scatter, and let's just give these names so we know that the first is set X label, I think. Wasn't it set X label? Oh, it's not evaluated yet. Okay, I'm just gonna say set X label and say first PC. So that's the x-axis, and the second one is going to be y label. The y-axis, I can't type today, is the second PC. And let's actually plot this, see what it looks like. Well, at least it separated the points and put them outside the kind of it spread them out, and there seems to be nice separation. So we could kind of, if we knew which one was which, maybe it would make sense. So the good thing is, if you remember, we actually had in digit data something called target. So for these 1790 whatever points, we actually know what digit each one is. So for example, target, let's look at the first 100. Okay, so the first one is a 0, second one is a 1, etc. to 9, and then it starts all over again. So the first 10th, every 10 it repeats. So what we can do is scatter plot can actually color these points for us. You can give it a C and say, given an array with different values, and it will just pick colors based on those values. So we'll say digit data, color them by digit data. This thing won't go away anyway. Data targets. Let's see what it looks like. What did we mount? It's target. Okay. And we don't need this cell anymore, so we'll get rid of that. So let it plot that. Now it makes more sense. There's clusters of different things. Maybe you want to see it kind of more clearly. You can change the color map. Obviously, you can do something like gray. In that case, it will all be shades of gray. We'll use rainbow, for example, which should give them bright and different colors. Okay. So you see, for example, here, this group is a different color actually than that group if you use the original color map. Sorry. If you use the original color map, maybe I'm colorblind, but it seems like then these two groups are the same. So now we have some idea, and it actually did cluster different digits together. We don't know which is which, but we can also get that. So this is kind of hacky, but what I'm going to do is I'm going to get this scatter object separately. Let's see if this still works. And put a legend on this saying on these axes, put a legend, and that legend is going to be the destructured scatter dot, I don't know what it was called, say legend, yeah, legend elements. Okay, so this what this does is it takes the different classes that you gave colors to from the scatter plot, and then opens it comes in as a array and opens that up and puts it into into a legend. So let's look at it like this. Okay, so oh, this is a function. Sorry. Let's make it a bit bigger. Maybe 15 to 12 or something like that, so we can see it more clearly. Okay, so when you look at it, it starts making more sense. For example, the ones which are these guys over here are seems to be in this space similar to the orange ones, which are the sevens, which obviously is the case, right? So a 1 looks like a 7, an 8 over here. Well, 8s seem to look like everything, so they're scattered all about, but the 9s are over there, and they seem to look like 4s, which makes sense, like the top space and then a tail, top space and then a tail here. Um, zeros, it says it looks like 6s, which I've made that mistake many times. So as you can see, just with straight PCA, we can actually make a pretty good visualization of our data with just 2 dimensions. And remember that the original data was 64 dimensions. So there are much better demonstrations of this using the same data and showing how different principal components affect different parts of the digits. I'll put links of those into the class site, so if you have time, you can take a look at those. I think this illustrates how to use PCA and kind of to get you started and figure out how you can use this in your own stuff or follow kind of more complicated notebooks and examples. Just one thing I want to talk about before I move on. The thing I did here, the scattered legend elements, basically this is kind of something Pythonic. When you run that, notice that it gives you an array of kind of the names of the things, and these are in math notation, so the labels, and each one of these objects is the color for that label. So when I say take this and give it to legend, when I put the star in front of it, it opens up that array and gives it as arguments to legend, so legend can know that there is the color purple and it corresponds to 0, there's the color blue, it corresponds to 1, and so on and so forth. Okay, so let's move on. Second thing that we talked about this time was kernel PCA. So as powerful as normal PCA is, it has problems separating non-linearly separable data. So if you have data that's kind of not possible to separate with a line or not linearly distributed, and then kernel PCA will be of less help. To be able to kind of try that, I'm going to try and create a dataset generator that will create the type of data that excuse me, PCA can't really do anything with. So what we're going to do is create a function that will actually create concentric spheres, things like this, right? So in 3-dimensional space or in 2-dimensional space, it will create concentric circles. For example, a thing here and then another circle here. So dots distributed like this with a gap in the middle. If you work in 3 dimensions, it will create a bunch of dots in the middle and then a gap and then a sphere shell around it and so on and so forth. So what I'm going to do is I'm going to create a little function called make shell. And what this make shell will do, will generate the number of points I want arranged in that fashion. So arranged in a circle if it's 2-dimensional, but we'll make it general. So if we say 2-dimensional, it will generate a circle of points. If not, it will generate, if we say three-dimensional, it will generate a sphere, a hollow sphere of points. If we give it more dimensions, it will generate kind of hyper shells that we can't really visualize. So the first thing it will have is the number of points it will generate. So let's call it, by default, if I don't say anything, it generates 100 points. I'll also say we'll give it the number of dimensions. So actually, let's give these names. Let's call this num points and dimensions. This is kind of verbose, but we'll give it a scale. So it will, essentially the radius of the sphere will be, let's call it radius. Radius will be, for example, 1.0 if nothing else is given. And we also need the thickness of the sphere. Since it's not a full sphere, it's a shell, it will have a certain thickness. So what I'm going to do here is I'll create a list of points. So what we're going to do is, if we go back to the previous thing, there was a nice figure there, concentric spheres. Okay, so if you look at this picture here, now what we're going to do is randomly generate points in this square, okay? And if they fall outside of this shell, this gray shell that we want, so if they're more than, if the radius of the point when we calculate it from the origin, if it's more than this outside R, we'll throw it out. If it's less than this inside R, we'll throw out that point as well. So only the random points that remain will be points within this gray area. So the way we'll do that is we'll create this list of points and we'll say generate so many points that you fill up this number of points. So we'll say while length of points is less than num points. Keep doing this, and we'll generate a candidate point. Let's call it point, and the way we'll generate it is we'll say numpy random, give us a random number between 0 and 1, and we'll multiply that by the radius. One other thing is, this point is, we don't know how many dimensional it's going to be. It's given by dimensions, so we'll say give us a random thing of size dimensions. So just to see how this works, if you're not familiar, if I say random size 1, obviously I get a single number, and every time I call this, I'll get different numbers. If I say random size 2, I'll get a vector of 2 things. So this works conveniently. If I want 2-dimensional points, random size 2 will give me 2-dimensional points. If I want 3-dimensional points, it will give me a random coordinate of 3 dimensions between 0 and 1. And if I multiply that by radius, if let's say I want to work on a radius of 4, it will be between 0 and 4. So that's actually what we need. So we'll start with this, and we'll say, so now you have this point, calculate its radius. Now we have a problem. We have 2 radii. Let's call this R, or let's name it something good. Let's call it at radius. So where is this point when you kind of put it in the coordinate sphere, and how far is it from the origin. Actually, let's call it dist from origin. Okay, so the way we'll calculate this is obviously if it's one-dimensional, the distance from our origin is the number itself. If it's two-dimensional, we have kind of Euclidean distance. We'll say the first dimension squared plus the second dimension squared and take the square root. If it's three dimensions, we do the same thing. First dimension squared, second dimension squared, third dimension squared, add them all up, take the square root. So we'll have NumPy do this. We'll say take the point and take the square of all its elements. Remember that NumPy, if you apply an operation on a NumPy array, it will broadcast to all elements. And then take that point, that squared point, and take the sum of it. And then finally take the square root of the same, that sum. That should give me the distance of this random point from the origin, which should work. And then I'll say, now is this point useful to us? Is it within the shell or outside the shell? That's easy to check. I'll say if distance from origin is less than the radius, and if the distance from origin is it has to be less than distance, but it has to be more than the inner shell. So it has to be radius minus thickness. Okay, so if this point is somewhere inside that circle I want, its radius will be smaller than the smaller radius, the outside radius, and its distance from the origin should be greater than the inside radius, which is the outside radius minus the thickness. So if that is true, then I'll just append this to my list of accepted points. So let's say accepted points. If not, I just move on. The loop goes back and does it again. So let's return this list of points, run the function, and let's try make shell. If I don't say anything, it should just give me a list of 100 points in 2 dimensions. What is this? Oh, okay. It's giving me one thing I forgot to do is convert this into a NumPy array, because that's what we were going to use later on. So let's see if it works now. We're stuck, so we forgot to do something. Actually, it won't allow me to stop it either. Cell is already running. Okay, I don't want it to run. Let's get rid of that cell if we can. I think I've reconnect. Restart runtime. Hello. I'll interrupt execution and restart runtime. Yes, I do want to restart the runtime. Okay, we don't need to do all the stuff before. Oh, actually, we need to import this stuff again. While we're at it, let's just do everything, even though we don't really need it. just so we know that the notebook still works. And let's evaluate make shell, and let's try again. Yeah, it gets stuck. So let's see what we did wrong here. Stop that, or it'll stop by itself. Let's see, we have our points. We said that has to be less than number. While it's less than number of points, do this. And if distance from origin is less than that, and let's see, what am I missing here? Okay, let's actually debug this online. Let's see what it returns. So I'll just get rid of the while loop and see what it does. Well, syntax, oh yeah. Points is less than number of points. We did that. What am I missing? Size is dimensions times radius. Distance from origin is that. Okay. Distance scale. Okay, let's just give it a small number of points, see if it still doesn't want to work. Num points is 1. Okay. NP, oh yeah, I have to re-import this stuff. And let's see if our make shell works this time. Whoa, okay. That's part of our problem, I think. Oh, points append points. Sorry, that's the problem. It has to be points append point because you had a point here and points there. Sorry about that. But it's kind of a good example of what kind of stuff that can go wrong. So yeah, this actually seems to be working now. Let's try it with 100 points, see if it still works. Okay, so let's say this is our test data, and let's plot it to see if it's actually true. We're getting a nice circle. Plot scatter test the 0th column versus test the first column. Here's another problem. We're getting only half the circle, or another quarter of the circle, because what we did here is we're taking this point between 0 and 1. So both sides of the point can only be between 0 and 1. However, we know that the coordinates can be kind of from plus radius to minus radius on both dimensions. So the way we're going to do this is we're going to shift this random part. So I'll take that into parentheses. I'll shift this by I'll say 2 times that random. So now it's generating points between 0 and 2 instead of 0 and 1, and then shift it by -1. So it will generate, this part will generate random numbers between 0 and 2, and this part will shift that one unit to the left or down depending on the dimension, and then scale by radius. So then it should work just fine. Yeah, so we have our little thing that makes shells, and the good thing about it is I can say make shells with more points. Oh, it's not called num, it's called num points. Yeah, it's a very nice dense sphere. I can change the radius. Let's say the radius is now 0.5. Obviously this plot will auto scale, so but you see that it's between 0.5 and minus 0.5 on both axes. I can probably change the thickness. The default was 0.1. Let's make it thicker. Let's say 0.25, so half the thing is here. Yeah, seems to work. So now let's create some test data out of, actually use this top thing. Let's call this our data. And what I'll do is create concatenation of 3 spheres or 3 circles. First one will have number of points, and radius will just be the original thing. So radius 1, thickness 0.01. The second one will be make shell of n 1000 points at radius 0.5. And the last one will be a make shell. Let's say that's the smallest circle at radius 0.1, and we'll do that. And these have to be, I think, in a tuple, and concatenate them on axis 0, so meaning combine them row by row, not column by column. So we'll get our data like this. Unexpected key. Oh yeah, keep reading. Normally, if I wrote this code myself, num points would just be n. Just to make it more explicit, I'm making it num points. And now let's see what our data looks like when we plot it. Very nice. So we have our 3 concentric circles. The good thing about this is now we can actually say dimensions is equal to, for example, 3. And do this for all the little shells. And for this one as well. Then obviously now you can't really plot it on a 2-dimensional thing. You could probably see a 3-dimensional plot. Even then you'll get confused because these spheres are within each other. So what happens if I take this data and also let's create a target thing for ourselves so we'll know which one which points belong to which sphere. We know that the first 1,000 points is the outer sphere, the second 1,000 points is the middle sphere, and the last 1,000 points is the last sphere. So we'll just say, actually, let's call this D and say D is equal to 3 for our example. And what we'll do is the target is an array of ones. Yeah, okay, so the first label is 1 and we have 1,000 of them, plus the second label is a 2, we have 1,000 of those, and the last label belonging to the innermost sphere is number 3 with 1,000 things. And now if I say color these by the target, we should get different colors. 3,000 elements, this size 1. Okay, so what does target look like? Did I make a mistake here? Didn't look like it. Okay, let's get rid of that. So let's see what it says. 1, 2, 3, invalid RGB argument. Huh. Did I miswrite something over here? Let's see. This should work correctly. I don't give the target. It should work fine. Oh, we broke something. Yeah, it's number of points, not. Oh, sorry. That's my problem. We'll take these. I'm gonna post this video with all my mistakes and everything. Please let me know if you don't want to wait for the mistakes. Then I'll try to edit those out for the future lessons. Okay, so now do we get the spheres? Yes. And do we get the colors? Yep. Okay. So now it kind of paints these things inside. Let's see what we can do with this three-dimensional sphere with PCA. So our original thing is we'll start with PCA again. We'll fit our data, and then let's steal our own figure thing from here and try to draw a figure. So we'll scatter the axes. I probably won't need the legend elements, so let's get rid of those parts. So P transformed, in this case, it's no longer digit data, but it's just our data object, our data array, and the color is just the target. So let's see what PCA does. As you can see, PCA doesn't do anything useful. It kind of renormalizes data, so it spreads it out. But again, all the points are within each other, so it's not really separating anything. And if this was dense enough, you wouldn't be able to tell different spheres from each other. Or at least you'd get the wrong idea. You would think that they were kind of coexisting in the same space, whereas as we know in the higher space, they're not coexisting. They're shells within each other. So now the question is, how do we do this with kernel PCA? So instead of kernel PCA, the object you want to use is kernel PCA, and when you look at the parameters, it looks very much like PCA. Again, you can give the number of components, which we don't use, but now you can define a kernel, and that default kernel is linear. So if you just drop in kernel PCA instead of PCA, it will do about the same thing. And just to show that, fit data and run it again. It's taking a bit more time, obviously. Maybe I put too many points, but basically you get the same result. Now let's say with kernel PCA, I would like to use a Gaussian kernel because I know that different spheres have separation from each other, so they kind of form neighborhoods. So kernel is, I think it calls it RBF and not Gaussian, but you can always check. Kernel can be linear, polynomial, RBF, sigmoid, cosine, so on. We want the RBF one, that's the Gaussian. So RBF, fit it with the RBF kernel, and then once you're finished, let's plot. Okay, first PC, second PC, we didn't get anything any different. So what might be happening here? Remember from the slides and the lecture part that you generally have to do some, because the RBF kernel has a tunable parameter, if you remember, something we called gamma, right? So gamma was, for the Gaussian kernel, it was essentially 1 over 2 sigma squared was equal to gamma. So the kernel, you have to kind of decide on what the value of gamma should, or sigma, if you're thinking in Gaussian terms, or overall what the value of gamma should be. So when you look at it, if you don't give it any gamma, it will take some default gamma. So let's see what that gamma is. You can always go to the documentation in these cases. Okay, so let's see. It has the kernel, and there it is, gamma. So if you don't give it anything, it says 1 over number of features. So in our case, number of features, since this is three-dimensional data, is 3. So it's taking a gamma of 1 over 3, which probably doesn't work. When you think about it, it's 2 sigma squared is equal to 3 then, which means sigma squared is about 3 over 2, and it just doesn't kind of doesn't work. So at this point, you can do tuning. You can make take a sense of what's happening and kind of what the distances are and so on and so forth. Or you can just use the trial and error approach and try a different gamma. So instead of 1 over 3, let's say I use a gamma of 1. Fit it with this. And hopefully, if I run it now, beautiful. See what happened? Now the gamma is such that basically 1 gamma means 2, the variance is 1 over 2 or something like that. And essentially when the variance is 1 over 2, the standard deviation is much smaller. Now it can actually distinguish the differences between the 3 spheres, the three shells. And you can kind of try this and see what happens if you go up with higher and higher gammas or lower and lower gammas. So let's say we go the other way and try and run this. At this point, it's essentially the whole thing becomes a single sphere, so it can't really a whole hyperbole, so it can't distinguish. If you go too high, then you have another problem. Let's say I have a gamma of 100, which means notice that if gamma is 100, this standard deviation has to be very small. Then it becomes essentially every point for himself. So now only the inner sphere is separated because that's the thing that fits into that hyperbole, and everything else, the outer two spheres, the outer two shells get concentrated as a single point. And you can kind of try different versions of this. So 10 will be probably a bit less drastic. Sorry. Actually, 10 kind of works. So you can kind of figure out if it's 10, then with a quick calculation, uh, two, two variance is 1 over 10, right? Which means the variance is 1 over 20, and that allows it to kind of separate these three spheres. So actually, there's a good range at which you'll still capture separation, and this kind of shows you a good example of why you should kind of be aware of your parameters when using these methods, because the default parameter might give you something that doesn't work, even though kind of potentially it could work. So when you have tunable parameters on these models, if you can make sense of them analytically, try to pick the best spot for that parameter, or if not, at least do a sweep of the parameter range if you can to see if you get different behaviors. One last thing before I end this, I want to kind of give a nice kind of demonstration of the curse of dimensionality we talked about. Remember how this function works? It kind of creates candidate points, and then if they are in a shell, they it appends them to the thing. So if I work three-dimensionally, it completes very fast. If I go to 5 dimensions, uh, it still works relatively fast. And notice that even with 5 dimensions, you can actually, kernel PCA should be able to, well, it won't be because we gave it the wrong gamma, uh, should be able to separate these. So let's try a gamma of 1 again. Even in 5 dimensions, you'll get decent separation. Yeah. And if I look at the actual thing, now it's kind of more crowded. So 5 works as well. It doesn't have to be 3 dimensions. As long as you kind of do the right gamma, you should be able to separate a data like this. So one thing I wanted to say before I ended this video is, so 3, 5 works. What happens if I say, for example, 20 dimensions? Notice what happens. It's working and it's not done. And it's taking its sweet time. And try to think about why that would be. Why it works very fast with 3, 5, but kind of keeps thinking about it with 20. Again, going back here, notice that it's creating points and then testing them, and only when they fit the shell it will append those points to the final array, and it has to find 100 points like this, or in this case, 1,000 points for each shell. The problem is when you're a 20-dimensional space, like we said before, all distances are kind of too large and nothing is meaningful. So what you're trying to do is trying to randomly get a point that falls into a rather narrow region in that space. So what it's doing right now, it's constantly trying new points, and they constantly don't kind of fit that region. So they get thrown out. It does new things. So this kind of nicely shows you what happens to the space and how unintuitive it becomes when you go to higher dimensions. Okay, so this is kind of the exploration of PCA. We'll come back for t-SNE, or rather stochastic neighbor estimation in t-SNE in a while.